So hello students, today we'll start the last unit of our subject irrigation engineering. So unit number 5, which is regulation and cross drainage works, waterlogging and land reclamation. So the first topic is, that is topic number 1, is regulation works. So regulation works. First one is canal falls. So a canal falls or drop is a masonry structure constructed at a point where the bed level of the canal is to be lowered. Alternatively, the lowering of bed can be achieved in a small length by providing very steep slope of the order of 1 V is to 10 H. V is the volume and H is the height to the canal bed, which is called as rapid. Next, necessity of canal falls. Why do we need canal falls? So when the slope of the ground is suddenly changed to a steeper slope, the permissible bed slope cannot be maintained. It requires excessive earthwork in filling to maintain the slope. So in such a case, canal falls are provided to avoid excessive earthwork in filling. Usually the bed slope of the canal is flatter than the general ground slope. So that also in longitudinal direction. So this occurs more often in peninsula where the ground slope is steep. In the ridge alignment of the canal, necessity of fall often arises. Next, location of canal falls. So on the downstream of the point where the canal bed level and ground level are equal, the bed will be banking. So the height of the banking keeps on increasing. A canal is high, that is greater than 2-meter banking, poses problems like heavy seepage, settlement, cracks, etc. Hence, it is necessary to lower down the bed. This lowering is achieved by the canal falls. Economical and safe location of the canal fall is between the vertical drop to the design slope. Fall can be easily combined with a cross regulator or a road bridge. If there is a takeoff point nearby, the likely site of the fall should be located on downstream of the takeoff and combined with a cross regulator. So in here you can see the location of a canal fall which is having a vertical drop on the available ground slope, and above the available ground slope, the slope that we design are also shown. So various types of canal falls. Falls are classified on different bases, such as number 1, controlling upstream water level in 3 classes. These are falls that maintain normal depth, discharge relationship, fixed upstream water level, and variable upstream water level. Number B, important shape characteristics as vertical drop, glacis, and stepped. Number C, which includes others, are well, chute or rapid, flumed or non-flumed, metering or non-metering. Next, regulators. So canal regulation works are the structures constructed to regulate one or more of the canal parameters like discharge, velocity, etc. So the different types of regulators are total of 7, which I have explained below. The first one is a head regulator, which is used to regulate discharge entering from one canal into another canal along with proportional quantity of silt. Next, number 2 is cross regulator, which is used to maintain necessary depth on its upstream, irrespective of the discharge flowing in the canal, so that the taking of canal can drain its full supply discharge or close the canal on the downstream. Number 3, falls is used to regulate the bed gradient and hence the velocity of flow. Number 4, escapes, to divert the entire canal discharge to waste when the canal on downstreams is to be closed. Number 5, outlets, to regulate discharge entering a farm. Number 6, silt ejector, to eject the silt that has entered into a canal from the diversion weir headworks. Number 7, silt excluders. It is used to exclude silt coming along with the river flow before the discharge is diverted into the head regulator and hence into the canal in a diversion headwork. So already for the case of regulators and diversion headworks, I've already shown you 2 to 3 videos, or I think more than that. So you can go back to those videos if you want to relate to any. Next, silt control devices. The 3 components that are employed for silt control at the headworks are scouring sluices or under sluices, silt pocket, and silt excluders. Next is canal outlet. Canal outlet is like a head regulator for a field course or water course. Throughout the outlet, water from canal, that is the distributary or minor, enters into the field course. The water course is a canal owned and maintained by the village irrigation panchayat, which is an organization, or by individual farmers. The discharge of an outlet is less than 0.085 cumex. The functions of outlets are to allow required discharge into the fields, to regulate the discharge according to water level in the parent canal, to measure the discharge passing out through an outlet. According to IS 7986/1976, outlet structure should satisfy the following requirements. The first one is it should be strong, simple with minimum or no moving parts that require continuous maintenance. Number B, it should be tamper-proof. Number C, the cost should be minimum. Number 4, it should be possible to divert proportionate quantity of silt. Number 5, it should draw full discharge even with low or varying head in parent canal. So these requirements are aimed at fulfilling the following functions of an outlet. Number 1, to allow predetermined discharge into the field course. Number 2, to draw proportionate amount of silt. And number 3, to measure discharge. Next, location of canal outlet. The irrigation outlets are located on distributaries, sub-distributaries, and minors. An outlet is not located or permitted on large capacity canal or canals kept charged throughout a season like main canal and branches. The outlet is located at a point where the ridge crosses the parent canal. It is preferable to locate the outlet on the upstream of a fall. Next, escape. Escapes are structures constructed on main canal and large branches. The object of an escape is to divert the entire canal discharge into the waste canal. This is required to cut off the supply in the lower ridge or if the head regulator is open to admit silty water into the canal, the same is diverted into waste a small distance away from the dam. An escape is located on one bank of the canal just upstream of the cross regulator and near to a cross drainage work. Escapes are of three types. Number 1 is surplus escape, number 2 is tail escape, and number 3 is cowering escape. So first one, surplus escape. It is also called as regulator type. In this type, sill of the escape is kept at canal bed level and the flow is controlled by a gate. This type of escapes is mostly preferred nowadays as they give better control and can be employed for canal maintenance. Next, tail escape. It is provided at the tail end of the canal and is useful in maintaining the required full supply level FSL in the tail reaches of the canal and hence they are called tail escape. Next, scouring escape. This escape is constructed for the purpose of scouring of excess silt deposit in the head reaches from time to time. Hence, it is called scouring escape. So, this is your assignment for lecture number 54, which is you have to explain about the silt control devices. So, here you have to explain in detail. So, you have to explain in detail about the silt control devices and the last date of submission is mentioned here. Now we'll go through a video. We'll continue with our previous videos where we stopped last class. So that's all for this lecture. Now we'll just go through the video.
Is equal to root over, say, tau s square a square plus w dash square sine square theta. Well, so that is what our disturbing force. So I'm writing this as F1. Well, then when there is a disturbing force, then if it is not moving means there is a resisting force also. And at a time of just incipient motion condition, these two forces, what we mean by incipient motion condition, that particles are just in the verge of motion. It is just in the verge of motion. So what is that? The disturbing force is just equal to the resisting force. And our interest is to find out permissible stress. Means up to that point, when our forces, when our particles are not moving, then we are fine. Our channel design is fine. So that we are talking about that situation. And of course, our permissible force may be a little less than this particular force, but when it is just in the verge of motion, then we can call that as a critical condition. And the permissible condition should not be the critical condition. It should be a little less than that. But anyway, let us see what is the expression for this critical condition. And so considering incipient motion condition, what we can have. Say considering incipient motion condition. We did discuss about incipient motion condition earlier also. That will equate, but the resistance force. First we have find out the disturbing force, then resisting force. The resisting force Because why we are writing this, that considering incipient motion condition, now resisting force, as we know, that it is coming from the frictional resistance here, and the cohesion part we are not counting in this point. So for resisting, because we are talking about alluvial channel, and this resisting force will be proportional to, suppose your force exerted is increasing, proportionally the frictional resistance is increasing, and of course beyond a particular limit it cannot increase, and that is the limiting condition. Well, so at incipient motion condition this will be at its maximum. And what we can see, that suppose this is the bed, this is the not bed, this is the side, then this will be opposing this motion, and frictional motion opposing this particular force, that will be the normal weight or normal reaction. So this will be having a normal force in this direction. Okay, let me draw on this piece because we are seeing it from the back side. Okay, that is fine, we can see it. So in this direction, in the normal direction, what will be the component? This is W cos theta. And as we know, the frictional resistance will be in any direction. We can say the frictional resistance is equal to mu into the normal force. So that normal force is cos theta. Weight is this one, so reaction will be like that, and then it is mu into cos theta. Okay. So this mu cos theta is basically opposing these forces. Now I'm not drawing exactly the direction here, but we can say that this is say mu cos theta. Now what is mu? That is, again, we need to refer to the frictional property of the soil. Okay, so but let me write here as mu cos theta. Here itself I am showing on this face, it is easy to show, and here just I am drawing it because that is, we cannot see the back side from this side, that's why I am drawing it here. Well, so this is equal to mu cos theta. Resisting force F2, if I write, this is equal to mu cos theta. Now, if angle of internal friction of the soil is say phi, then what the mu is, that we all know that mu is nothing but the tan phi. If the angle of internal friction is phi, then it is tan phi. So we can write that, this is not cos theta, this is W cos theta. This I did a mistake in writing here. This is not cos theta, this is W dash cos theta. Again, dash is always coming, W dash cos theta. This effective weight of the soil will be significant there. So this will be, this I should write as mu W dash cos theta. Okay. This will be W dash cos theta. Well, and this mu we can write, as I have explained, that this is equal to tan of phi into W dash cos theta, where phi is nothing but angle of internal friction, Well, so now for incipient motion condition, we can equate these two. So equating these two, what we can write, that W dash cos theta and tan of phi. This is what the resisting force, and the other one is say tau s a plus W dash sine theta with a root sign. Then squaring these two, what we can write, that W dash square cos square theta tan square phi is equal to tau s a. Just to, our target is to separate this tau s, and then this is the tau s square. These were also square because after taking square only we were taking the root, so it will be tau square a square W dash square sine square theta. Well, now this expression where we got is this one, tau square a square dash square w dash square sine square theta. We are writing the same expression here. Okay. Then from here what we can write, that tau s is equal to, that is the side tractive trace, we can write from this part as w dash cos theta tan phi by a. First we are writing tau s is equal to this minus that, and then we are taking w dash cos theta tan phi common, and then of course we are taking root, and then if we take the other part here, then it become 1 minus tan square theta by tan square phi. Well, so when we took tan phi common, then here we are having already, say, tan square phi is coming here, and then it becomes, and we are taking cos theta common, so it is becoming, in fact we took cos square theta, so that way it is becoming cos sine square theta by cos square theta, so this tan square theta is coming, and then later when we took root over, this cos square theta become cos theta, tan square phi become tan phi, and all are just getting this. Just one more step we could write in between. Well, so that way we are getting this tau s, the side tractive force. We are getting an expression. Let us give a number 1 to this equation. Well, now if we talk about the shear stress at the bed, so shear stress, or rather let me use the word tractive, unit tractive stress, unit tractive stress or tractive force, unit tractive force, because already we are using the term unit. So tractive force at bed. Now what is the difference between this particular expression in bed and side? Well, if we talk about bed, then our theta for the bed is becoming 0. If we just flatten it, this become bed. So in bed, other things will be remaining same. This force will be there, the reaction force will be there, but here if we take a bed, same area, then this force will be there, and this is tau b into a, then weight component will be directly vertical, so there will be no component in that direction, and then the resistance force will be coming here. It is directly equal to W. Means basically if we make theta is equal to 0, then we get the expression for